is this one. H is a subspace defined by this two linear equation. And there is this V in dimension 5 space. I ask you to find the basis of this B. That's the first thing you have to do. Some basis of B, solving this equation. And then this little v, basis of W, a basis of H, this little v is outside H, so W will form a dimension 4 subspace. And ask you to find this linear combination. There's a 1, 2, 3 linear independent vector outside this V, therefore is a dimension 4 linear combination. Especially I made this one negative 1. You have to find this A1, A2, A3 orthogonal to B. Okay? But once you find that, I was claiming that this A1, V1 through A3, B3 is the orthogonal projection of this V onto H. Good thing is that this V1, V2, V3 doesn't have to be orthonormal basis or orthogonal. If you just find this one, and that is the one. Alright, so first let me explain how to find this combination A1, A2, A3 such that this is orthogonal to B. Well, if you just, you have this V1, V2, V3 calculated already in this stage. By putting this inner product in here, you have three conditions. You know, this is orthogonal with the V1, orthogonal with the V2, orthogonal with V3. That's a three equation, linear equation on A1, A2, A3. So one way or another, it's not a big size, you were able to, probably could compute it. So here is the way I did it. It was easier to handle in the computer that I just let this, all the coefficient, these are the basis of W. H is this 3 dimension. I add one more, that's the W space, I have 4 dimensions. And I wanted this one to be orthogonal to the first 3 vectors, V1, V2, and V3. So that is this type of equation. This was really dot product. I realized it doesn't have to be the inner product. This is really dot product in a 5-dimensional space. So this one, together with that, you know it distributes. It's a dot product. So each of the equation with the vk in it looks like this: vk dot 1, v1, vk dot v2, and so on. We have this vector, and I have calculated this v1 and v2, v3, solving that equation using this augmented matrix or just a homogeneous equation using the row reduction. So I calculated all these coefficients. This and that one, that is just all vectors. I can dot them. There are these numbers. I'm solving this one for A1, A2, A3, and A4. So again, is this equation. So this is a reduction. All I want is I want to set this A4 equal to -1, right? And then again, it's 3 equations because 3 orthogonal conditions, and it's a 3 variable originally. I extended to 4. It was easier for me to do it this way. So I set A4 equals -1, and I solve this equation, and this is what I got. All these coefficients going backward. You know, that's how you do this row echelon form. So I got this. E tilde V1, A1 was 1, A2 was -1, A3 was 0, and this one was set to -1. So altogether it was this vector: -2, -1, 0, and 1, 1. Okay? So this is a vector perpendicular to which one, which one, which one? V1, V2, V3, right? What is a good name for this guy? The vector is like a cross product, but we don't know what how the magnitude behaves, so it's not. But that's the idea of the cross product, right? I give you 2 vectors in 3-dimensional space. You find one vector that's perpendicular to the other 2. If it is 4-dimensional space, which is W, and I have 3 vectors, and what is the vector that is perpendicular to all the other 3? That was one calculation in here. And I also have the cross product formula there. So I have that, and what was the condition here? You're supposed to show that this first 3 combination, V1 minus V2 plus V3, is a projection, right? That was a part 2 question. You're supposed to show that this A1, A2 V2, A3 V3 that I've just calculated here is really the projection. Okay? So what was the theoretical description of that projection? Anytime if there's u0, which is v minus u0, is perpendicular to everything in H. Wasn't that the projection? Right? Remember that theoretical description? There is this vector u0 such that v minus u0 is orthogonal to everything that is in H. Everything that is in H is v1, v2, v3. If they're orthogonal to the 3, the all linear combination is 3. So we're looking for that. As see here is a v minus. This is actually something minus v, not v minus, but that's just a negative. And that's this vector u e tilde in here. So v minus u0, if I call that one u0, then it's negative e tilde. So v minus u0 is negative e tilde. E tilde is always perpendicular to v1, v2, v3, right? Negative, you can factor it out. It's a scalar. So I guarantee that this v minus u0, if I set this thing u0, and this condition is satisfied. Does that make sense? If I set this one as u0, v minus u0 is always perpendicular to everything in H. Therefore, that u0 must be projection, because there was one and only one vector that has this property, right? That was a theory. That must be the projection. Okay, so if you plug in this number, -1, 1, 3, -1, 0, that must satisfy that condition that I started with in here. It must be a vector in H, and that is the closest one to that V, and so on. That was a projection. Any question about number 4? What is the next one? This was a hard one, actually. So I guess we start with this function.